How's it going, guys? Derek Craig here with oilfieldbasics.com, and today we're going to be talking about the basics of combustors. We're going to begin by talking about why we use them, where we find them, and then we're going to go into the different types and also into the components of a typical combustor setup. In order to make this video most beneficial for you guys, Sebastian and I went and met up with our friends at High Bond EDI. Specifically, we met up with Corey Haney. He is their applications engineer, and he is the one that designed their combustor from the ground up, from scratch. So we went and met up with him, and we're going to have clips of him and his discussions and his explanations featured in this video. Now, Corey really did you guys a solid and created a 101 guide to combustors, which we're going to have below this video on our webpage. So if you're viewing this on our website, check below and download that guide. All right, so diving right in, let's now take a look at where combustors are used and where you might find them. So typical application is going to be on a common well pad. So combustors are used on the production phase of a well. So after the well has been drilled, after it's been completed, typically hydraulically fractured if you're talking about the shale wells here in the United States. And on a well pad, this might be what it would look like. So on your wellhead, your hydrocarbons are coming through your wellhead being produced at surface at a high pressure, let's just say 800 psi in this example. So from the wellhead, they're going to go into a separator where your gas is going to be separated from your liquid. As soon as you have a pressure cut anywhere along the stream and where hydrocarbons are involved, you're going to get what we call flash gas. So there's actually gases that are trapped within the oil or the condensate, sometimes even the water, depending on the temperature and depending on the pressure. So anytime you have a pressure cut, you're going to get what we call flash gas. So the separator is going to take the gas and put it into the sales line typically, and then the liquids are going to be dumped into storage tanks. And again, this is a typical flow. It can be a little bit different, can be a little bit more advanced, but we're going to keep it simple for this demonstration. So the liquids, once they go to your stock tanks, these stock tanks can only be kept at ounces of pressure. So you might be going from a separator that has hundreds of psi of pressure on it to something that can even take a whole pound of pressure per square inch. So what that's going to create is a lot of flash gas. So this flash gas has to be taken off of the tanks, and then you've basically got two options. You can either recover the gas and use a compressor to actually compress that gas and send it back into the sales line, or you can actually destruct the gas and either flare it or put it into a combustor. Now, which method a company chooses is going to be dependent on a lot of things. It's going to be dependent on commodity pricing. It's going to be dependent on what type of midstream setup that they have. And it's also going to be dependent on the volume, and how economical it is. A compressor is going to be expensive to rent typically. You might require electricity, might not. The destruction, you might only be able to destruct so much. So if you've got a lot of volume, typically you'll see companies opting to recover it. If you only have a little bit of flash gas, or if your well's on the decline, you might just use a combustor or a flare. Now, whether a company chooses a flare or enclosed combustor, it's going to be dependent on anticipated flow rates, cost of systems, regulations, etc. Typically, flares are going to be cheaper, but they also don't commonly do as good of a job when you look at and compare destruction efficiencies with that of an enclosed combustor. Enclosed combustors are also more precisely engineered for specific flow rates, composition of gases, and line pressure. It is common to see more combustors and flares in states that are more stringent, such as PA, West Virginia, Ohio, and Colorado. And in states that are more strict, you might only be allowed to have an open flare on production facilities in a few particular cases. You'll typically see flares on locations where the well is being tested or where you have a chance of encountering unexpected gas, such as while you're drilling. And enclosed combustors are typically used in applications where the variables such as pressure, gas composition, and flow rates are all known. And this produces a better destruction efficiency. And now Corey's going to explain a little bit about how we regulate efficiency.
The design of the combustor itself has to make sure that it efficiently and effectively mixes the fuel with the air. But at the same time, you have to have high enough temperatures, stack temperatures, to maintain good constant destruction efficiencies. So the EPA regulates that they want to have at least a minimum of 1400 degrees in your Fahrenheit in your stack temperature. The reason that's important is that methane statistically has a minimum ignition temperature of about a little under 1400. So if you're hitting 1400, you are theoretically destroying everything that's in there, any hydrocarbon, because methane has the highest minimum ignition temperature. So by maintaining your 1400 degrees as a minimum and going above that within safely around, say, 2100 degrees, you are destroying everything effectively inside the combustor.
Next, I want to talk about the two different types of enclosed combustors. First one being mechanical draft and the second being natural draft. In order to get combustion, you need both fuel, which we've already established comes from the vapors on the tanks, and you need air or oxygen. There are two primary ways in which you can get the air required to combust the gases, either through blowing it into the stack mechanically, which requires electricity that most sites don't have, or you can let it occur naturally.
A natural draft combustor is typically the most common enclosed combustor that you're going to find in the oil and gas industry. The reason for a natural draft combustor versus a, say, mechanically actuated and automated combustor is that the airflow, the air being pulled into the combustor, is done naturally. The way that the airflow is pulled into the combustor is through what's called the stack effect. The stack effect is simply a difference in air densities. And when you have a difference in air densities, the air begins to move, begins to flow. Well, that's created in our application through strictly temperature difference. As the temperature within the stack begins to increase greater than the ambient temperature, you have a natural flow of air being pulled into the combustor.
Next, let's discuss the main components of an enclosed combustor system.
Good practices when it comes to looking for an enclosed combustor is that you would want to have some sort of, you've got to have your instrumentation, so you want to be able to sense stack temperature, of course. You want to be able to sense inlet pressure, because one, that, as we said previously, that directly affects the efficiency of the combustor. You want to have some sort of valve, emergency shutdown valve of some sort. It's not always an emergency valve, but we can use it to regulate the pressure coming into the system as well.
Now, continuing what Corey said about the ESD, you can see it pictured here right before the combustor. This is an important device to utilize so that if the pilot fails or if the stack overheats, that it can shut off the supply of gas and alert the operator.
You also want to have a flame arrestor. Flame arrestors are super important. And then, of course, a control system, some sort of the brains of the system. And then just going to the stack itself, you want to make sure it's insulated.
Now, we want to make sure that the stack is well insulated so that nothing that touches the stack on the outside will ignite or catch fire. Another crucial component is the pilot monitoring system. And here's some really cool insight into how that works.
There are two main ways in which a pilot is monitored. One, you have like what's called flame ionization. And basically what happens is that flame, in a sense, is a conductor. So there's a high voltage placed on one of the sensing rods that makes its way through the flame to ground, and once the controller recognizes that, it knows that there's a flame. If the flame is not there, it can't make its way to ground, therefore it knows that the pilot is not there, the flame is not present. The other way is like UV sensing, and that's an effective way to do it as well. It's either there or it's not. Typically that kind of hardware is rather expensive. Okay. But that's another way to do it. And I didn't mention a third way, and that would be based on temperature. If there is a minimum temperature where say a thermocouple is sensing that flame where the pilot ought to be, then it hits that minimum temperature that the control system is looking for, it will think that there's a pilot.
Now, Corey also mentioned that flame arrestors are utilized, and this is again a crucial device to maintain safety, and his explanation of what a flame arrestor is and how it works had me amazed.
Its purpose is simply to eliminate the potential for a flame to propagate from the burner backwards to its source. And the only way that a flame would actually exist and go backwards through the pipe is that if the fuel being supplied to the combustor has oxygen in it, some sort of oxidizer. You can't have a flame without fuel and oxygen, or an oxidizer. And so if in the event you have air in your supply line mixed with fuel and it's moving its way back at a speed slower than the flame can actually burn, then what ends up happening is that flame goes backwards through the pipe and back to its source, and very quickly that can turn into a very dangerous situation. It can explode instantly in some cases. But the way that the flame arrestor works is that there's crimped sheet metal inside of there, very thin, very light, sometimes aluminum. And what it is, it increases its surface area by being crimped in a circular fashion. And as that flame propagates backwards, it acts like a very efficient heat sink. It's pulling that heat away from the flame so it can't keep going backwards. The minimum ignition temperature has been removed because it's absorbing all of that heat so effectively. That's why if you look at a flame arrestor, they should have a minimum burn time on there. That if a flame were sitting here for X amount of minutes, that flame would not be successful in going past the flame arrestor for a certain amount of time.
See what I mean? I can't top that. Another crucial component that we want to touch on is the knockout pot. Now within the waste gas piping system, there should always be a knockout pot between the tanks and the combustor, and this line should be sloped both ways towards the knockout pot. The knockout pot allows for any liquid hydrocarbons to be collected so that they don't get into the combustor and cause issues. Now that's enough content for one video. Part 2 to this video is going to be covering placement, design, and troubleshooting. So check that video out, and also be sure to check out our other materials and courses available at oilfieldbasics.com/learn. If you want to learn more about the production side of this industry and how a well is produced or how it was drilled, completed, and everything, check that out, oilfieldbasics.com/learn. And also please be sure to follow us and subscribe to us on our various social media platforms so you will be among the first to know whenever we drop new content.